This is part 4 of derivatives and the shapes of curves. We are going to pick up with question 8. Question 8 is asking us to find the local maximum and minimum values using both the first and second derivative tests. So let's see what we can figure out. So if we're using both the first and second derivative tests, that means we need to take the derivative. So let's start with one piece at a time, and we'll look at how we can use both of these tests. So if we need the first derivative, that would mean that we are taking our derivative of f of x equals x to the fifth minus 5x plus 3. So our first derivative would look like f prime of x is equal to 5x to the fourth minus 5. So we've got our first derivative. Then we've seen that to use the first derivative test, we need to set our first derivative equal to 0. So 0 equals 5x to the fourth minus 5. If we solve this down, now be careful. The common mistake, well, one option would be to add 5 to both sides, and I'll show you. So 5 equals 5x to the fourth. Then you would divide, so you get 1 equals x to the fourth. Then you need to be very careful because you need to take the fourth root, which will give you positive 1 and negative 1 equaling x. Another option would be instead to look and see that you have this 5 in common, so pull the 5 out. And if you do that, you'll get x to the fourth minus 1 equaling 0. Well, x to the fourth is a difference of squares, and you can factor that. You can divide your 5 by both sides, so that goes away. So x to the fourth minus 1 can become x squared minus 1 and x squared plus 1. And then you could do it again because x squared minus 1 is also a difference of squares. So that would become x minus 1, x plus 1, and x squared plus 1. X squared plus 1 is never going to give us a 0 because it's going to always be greater than 0 because anything squared is going to become positive, and then adding 1, a positive plus 1 is more positive. So we're not going to get a 0 from x squared plus 1, but we will get a 0 from x minus 1, and we will get a 0 from x plus 1. So our zeros will be at 1 and negative 1. So these are the two places that we are going to get a 0. So that means when we look at our intervals, we are going to be splitting them at 1 and negative 1. So it'll look like this. So this would be negative 1 and this would be 1 when we're looking at our intervals. So we would have negative infinity to negative 1. We would have negative 1 to 1, and we would have 1 to infinity. So those are the splits for our interval. So now we need to look at the sign of f prime. So let's look at our sign. So if we are looking at negative infinity to negative 1, so we need to pick a number between negative infinity and negative 1. So maybe negative 2. So if we're looking at negative 2 and we put negative 2 back into our derivative, then that's going to look like negative 2 to the fourth, which will turn it positive, times 5, and then subtracting 5, so it will be positive. And then if we do the same thing, pick a number between negative 1 and 1, so 0 is in that interval, so that's kind of nice. So 0 to the fourth is 0, times 5 is still 0, minus 5, it's going to give us a negative. And then we need to do it again, so let's try this time, how about we pick positive 2. So that would look like we would have 5 times positive 2 to the fourth minus 5. So this is going to be a lot more positive than just subtracting off 5. So that's going to give us a positive value. Okay, we got that part. So now we need to look and see if this is increasing or decreasing. So increase or decrease. Well, if it's positive, that means it's increasing. Negative means it's decreasing. Positive means it's increasing. So this is going to be our min, and this is going to be our max. If we want to figure out the y-coordinate, then we need to put our -1 and our 1 back into our original equation. So that would look like f of -1 equals -1 to the 5th minus 5 times -1 plus 3. So -1 to the 5th is going to be -1 still. -5 times -1 is +5, +3. So it looks like if we are going to put all this together, we're going to get 7. So 1, 7. All right, now, -1, 7. Now let's do the same thing, but now let's do at 1. So if we're trying to find f of 1, let's get rid of these negatives in here. There we go. So 1 to the 5th is 1, minus 5 plus 3. So 1 minus 5 is -4, plus 3 is going to give us -1. So 1, -1. So now we have used our first derivative test to figure out our values for our max and our min. But this question is asking us to use the first derivative and the second derivative test. So let's try again, only this time let's use our second derivative test. So all of this is our first derivative test. So next we need our second derivative test. So if we need our second derivative test, then that means we need our second derivative. So let me go back over to here. And let's go to our second derivative. So we need a second derivative. So our second derivative is going to look like five times 4 gives us 20, x to the third, and the derivative of 5 is just 0. All right, and so let's see if we can figure this out. So we're trying to figure out our second derivative at our critical numbers. Well, where are we going to find our critical numbers? Our critical numbers are going to be where our second derivative equals 0. So how are we going to find that? Well, remember we just solved our critical numbers? And we said that our critical numbers, so our inflection points, the changes of concavity, is where our second derivative is going to be 0. Our critical numbers are where our first derivative is equal to 0. And we already found those. We found those at our -1, and we found those at our +1. So what we need to do is we need to check our critical numbers into our second derivative so that we can see what's happening at those critical numbers. Because if you have a critical number that is going to be less than 0, it'll give you a maximum. If you have a critical number that is greater than 0, it's going to give you a minimum. So let's check that and see. So if we take our second derivative of -1, that's going to look like 20 times -1 to the third, and that's going to give us -20. Well, we know that -20 is less than 0, so that's just going to be a maximum, which is what we figured out from our first derivative as well. It's nice that they agree. And then our second derivative, checked at 1, is going to look like 20 times 1 to the third, which is going to give us +20, and +20 is greater than 0, so that's going to give us a min. And that's what we figured out before. The piece that we need here is if your second derivative of your critical number is greater than 0, then that's going to give you a local min. And then conversely, if your second derivative of your critical number is less than 0, then that's going to give you a local max. There we go. So you can use either the first derivative test or the second derivative test. I like to use the first derivative test you still have to use part of the first derivative from the critical number piece in the second derivative test, so I'd rather just finish with the first derivative test, but you can use either. So let's try number 9. Find the critical numbers of f of x equals x to the 4th times x minus 1 to the 3rd. What does the first derivative test tell you? So this time it's just asking us for the first derivative test. All right, let's see what we can do. So if it's asking us for the first derivative test, that means we need our first derivative. This is going to be a product rule. See it right here? So our product rule tells us the first times the derivative of the second. So the derivative of the second means bring down your power, subtract 1, and then we have to use our chain rule on the x minus 1, and the derivative of x minus 1 is just 1. There we go. And then we need plus our second, which is x minus 1 to the 3rd, times the derivative of the first, which is 4x to the 3rd. Okay, we got all that. So now we need to see what we can do to try to clean this up. So if I look here, I see x minus 1 to the 2nd, I see x minus 1 to the 3rd. So I'm going to try to clean this up a little bit. So I'm going to pull that x minus 1 to the 2nd to the front. And while I'm doing that, if I keep looking, I also see an x to the 4th right here, and I see an x to the 3rd right here, and I'm going to pull some of that as well. I can pull x to the 3rd. So let's do all that. So let's pull that x to the 3rd. Let's pull that x minus 1 to the 2nd. And then let's write what we have left over. So if we write what we have left over, we have our 3 left over. We have, let's see, is there anything else left from this first one? We have an x from the x to the 4th right there. The x minus 1 we've taken. The 1 doesn't change anything. Plus, we have a 4 left over, and we have an x minus 1. All right, I think we got everything. So let's clean this up a little bit more. We can set it equal to 0, which means each piece can be set equal to 0. Do you see the 3 different pieces? Here's 1 piece, here's 2 pieces, and here's 3 pieces. They're all products, so each term of our product can be set equal to 0. So that means that x to the 3rd equals 0. That means that, oops, I forgot the equals. X minus 1 is equal to 0, and that means that, let's go ahead and clean this up right here. So that'll give us 3x plus 4x minus 4. So this means that 0 will be equal to x. This means that 1 will be equal to x. This means that 7x minus 4, so 4 equals 7x. So 4 over 7 is equal to x. Okay, we found our division pieces. So now we can create our intervals and we can see if we can simplify it all down. So we have 3 different divisions of our intervals. We have 3 different critical numbers. So that means that we're going to have to divide our intervals into 4. So we have, let's see, the smallest is going to be 0. So we have negative infinity to 0. Then we have 0 to 4/7. And then we have 4/7 to 1. And we are going to scoot this over so we can use the last little piece to have 1 to infinity. There we go. There we go. Okay, so now we need to figure out the sign of our first derivative in each. So we need to pick a value. We need to pick a value that is in each different interval so we can start doing some checking. So between negative infinity and 0, pick a value. How about negative 1? So if we put negative 1 back into our derivative over here, work it through, what are you going to get? Let's check our sign of our first derivative. Did you pause the recording? Did you check them all out? So if we are looking at negative infinity to 0, so I picked -2, it's in that interval, this works out to be positive. If you put -2 back in to your derivative, this is going to work out to be positive. Then, if you put between 0 and 4/7, so between 0 and 4/7, I picked 0.5. There's not really any nice values that work, so I picked 0.5. It's going to work out to be negative. And then from 4/7 to 1, I picked 0.9, and that works out to be positive. And then from 1 to infinity, I picked 2, and in this case, that also works out to be positive. So we have all of our signs of f prime. So that means now we can go through and we can figure out where we are increasing and where we are decreasing. So if it's positive, it's increasing, negative, it's decreasing, positive is increasing, positive is increasing. So that means right here at 0, we are going to have a local max. Right here at 4/7, we are going to have a local min. And then right here at 1, it was increasing and it's staying increasing, so that's not going to be a max or a min. So this is going to be our first derivative test, and it is going to tell us that we're having a local max at 0 and we're having a local min at 4/7. So this question is asking us, what does the first derivative test tell us? It tells us our local max and our local min. If we went on and did the second derivative test, we would have to find f double prime, and it would be a huge second derivative here with the different pieces being multiplied together with the product rule. It'd be a huge second derivative, but we could do it, and then we could work it through and we could find our second derivative and we could see what would happen at f double prime of 0, what would happen at f double prime of 1, and what would happen at f double prime of 4/7. So what would happen is if we put in 0 for our second derivative, we'll get 0. If we put in 1 into our second derivative, if we worked it all the way through, we would get 0. And if we put 4/7 in, we would find that 4/7 is greater than 0, so that would be a min. So it's not overly helpful for the second derivative in this case, because when we have our critical numbers of 0 and 1, because remember you put those critical numbers back into your second derivative to figure out if it's greater than or less than 0. So if we put our critical numbers back in, both 0 and 1 are 0. So that's not overly helpful in that case. So that's another reason why I like the first derivative test better. I feel like it's part on the way to getting to the second derivative test, but I also feel like in many cases it's more telling because I like the way we can have this little arrows up and down graph to help us see the maximums and the minimums. So there's question 9. Let's see if we can figure out what is happening in question 10. Question 10 says, let T be the temperature at time t where you live, and suppose that at time t equals 3, you feel uncomfortably hot. How do you feel about the given data in each case? So this is a scenario. We don't have a whole lot of information, but we are trying to use the information that we have to determine what's happening to the temperature. So let's just take what we know and fill in with what we can. So for the first part here, it is saying that you are starting at time 3, so t equals 3, and you feel uncomfortably hot, meaning you think it is too hot. We don't know what it is, but you think it's too hot. So let's see what we can deduce from the rest of the information. So in part A, we're told that the derivative of 3, so f prime of 3 equals 2. So what does that mean? Well, when we take the derivative, that gives us a slope. So we know that our slope at time 3, so after t equals 3, so wherever time that is, at that time, our slope is a positive 2, which means it is increasing. So your slope is a positive 2. So a slope of a positive 2 would be like up 2 spaces over 1, so a positive and increasing slope. So that means that your slope is increasing. If your slope is increasing, that means that you have a rate of change of 2 degrees per hour. So what have we figured out here? We figured out that our slope is 2, so it's increasing at 2 degrees per hour at whatever time equals 3. You already were hot, and now we found out that it is increasing and getting hotter. But beyond that, look at our second piece of information right here. We're told that our second derivative at 3 is equal to 4. So this means that not only is it getting hotter, but our rate of hotterness, if that's a word, is increasing. So that means that it is getting hotter faster. So it's getting hotter and it is getting hotter faster because we have our positive second derivative here. So I'm going to conclude that you are uncomfortable. And not only are you uncomfortable, you're more uncomfortable than you were before. So let's try the next one, part B. So what can we deduce from part B? Well, in part B, we are told that the derivative is still 2. So the derivative is equal to 2 at our time of 3. But look what happened. The second derivative, see right here, we've got that negative here. So what can we figure out? Well, our slope of our first derivative is 2, so it is still increasing. It is still getting hotter. So it is increasing at 2 degrees per hour. However, the rate of increase is getting slower because we have that negative 4. So it's increasing at 2 degrees per hour, but that rate of increase is decreasing. So what that means is it's slowly getting warmer. So you're increasing at a slower rate. So it's not getting warmer as fast as it was before. But it's still getting warmer, so I'm still going to conclude that you're uncomfortable. Okay, let's try the next one. So now, look, we have a negative right here. So what this means is after 3, t of 3, the rate of increase is going down. So our rate of increase is going down. It's decreasing at 2 degrees per hour. So that starts off pretty good. It was too hot, so it's decreasing at 2 degrees per hour. But look right over here. The rate of change for the derivative is positive 4. So what that means is even though it is decreasing at 2 degrees per hour, this rate of change is increasing, which means that it is changing our second derivative, so it's becoming less negative. So even though we have that increase of the 4, it is increasing the decrease, which sounds like a double negative here. But it was decreasing, but now it is going to start increasing. So our rate of decrease is going to become less negative, which means it's slowly getting cooler. So it's cooling less fast, if that makes sense. So it's getting less uncomfortable, if that is a characteristic. So getting less uncomfortable, but not very fast. So I'll say getting less uncomfortable. Okay, let's try the last one. So here we have a negative 2 and a negative 4. So what this means is our slope, our original rate of change of the derivative is decreasing. So it's going down, so it's getting cooler. Okay, we're okay with that part. But then it says that it is negative 4 for the second derivative. So that means that the rate of change is decreasing. So that means it's becoming more negative, which means that the temperature is beginning to decrease faster. So that means that it's finally cooling off, which means, theoretically speaking, you would be getting more comfortable. So this has been a look into the derivatives and the shapes of curves.